Hi, Algebra 2 Trig students, Ms. Shaw here, and today for your asynchronous work, we are going to be discussing another type of exponential growth, which is continuous growth. So this is the last and final formula that we're going to be talking about. Yesterday, most of you guys took the SAT, and on Monday, many of us assessed on exponential growth and decay, compound interest, and then some exponential graphs. So this is the last and final piece to that. We will not be assessing on this material, but it is important to know for our future. So when we talk about continuous growth, we're going to start off by looking at this table, which investigates the growth of a $1 investment that earns 100% annual interest. So that means that our rate is 1, okay? Changing 100% to a decimal is just 1.0. And we're looking at this data over the period of 1 year. So our time is 1. As the number of compounding periods per year, which is n, increases, our goal is that A value also is increasing as well, okay? So when we compound annually, right, we're investing $1 and it earns 100% over that year, we are going to be using the compound interest formula, which we see right up here, okay? N being what we're compounding by, okay? So it is a little bit different than the compound interest formula because there is no T there, but you know, this is just us trying to figure out the growth part of it, okay? And T is always 1, so really this is N times 1 constantly, and anything times 1 is just itself. So if we look at something that grows just once, it happens annually. 1 times 1 plus 1 over 1 to the first power is just still 2, okay? Well, if something grows semi-annually, we know that that's happening twice per year. So our new N value is 2. Okay, well, that becomes the value of 2.25. Okay? If something grows quarterly, that's happening 4 times per year. Okay, and that means that our N value is going to be 4. We would raise that to the 4 times 1, right? Because our T value is just always going to be 1 because we're looking at 1 year. And that becomes 2.4414. And then if something happens monthly, we know that that's happening once a month. So our N value is 12. Raise that to the 12th power, it becomes 2.61303. Daily, our N value is 365. Raised to the 365 degree power, and our N value our final amount becomes 2.71457. Hourly, well, there is 8,760 hours in a year. Okay, you take that by finding 365 and multiplying that by 24. So therefore, if we look at this, our N value would be 1 over 8,760 raised to the 8,760th power. And that gives you 2.71813, okay? And then last but not least, now we're going to get into something that's a little bit more continuous, right? Like if something happens once a year, it doesn't really happen that often. If something happens twice a year, it doesn't really happen that often. You know, if something happens 4 times a year, okay. Once a month, okay. Something happens daily, that's way more frequently. Something happens that's hourly, that's happening all the time. Something that happens every minute, okay? Well, that would be where our N value is 525,600. So 1 times 1 plus 1 over that value. Raised to that power. And that gives us the value of 2.71828. And then finally, if something's happening every second, that is pretty continuous. I mean, think about your day-to-day routine, your day-to-day plan, what you do, something that happens every single second. Like think of an analog clock, okay? An analog clock has the second hand and it's constantly ticking every single second. That's a continuous function. It never stops, like unless the batteries go out. That second hand is constantly ticking as it goes all the way around that analog clock. So that is something that is happening every single second. That is so continuous, like it never stops, right? And that value we can plug into the formula as 1 plus 1 over 31,536,000. Make sure there's enough zeros there. And then you would raise that to that whole power, which I kind of wrote very, very small, so that way it fits. And when we do that, we end up getting this value of 2.71828. We're rounding that to the 5th decimal place. Okay. Now, if you wanted to see what something like that looks in your calculator, 1 times 1 plus, okay, now remember, we want those parentheses for order of operations, 1 divided by 31536, 1, 2, 3 zeros, double parenthesis, and then we raise that to that same exact value. Now, if we look right here, we do get 2.718282473. So then we would just round right there, okay? So this n value, as we can see, in terms of like time, nothing really happens more frequently or as continuously as something that happens every second. So as n becomes very large, the value of 1 times 1 plus 1 over n to the nth power, remember our time is just 1 because we're just evaluating 1 year. It is going to approach this number that we refer to as E, okay? Now, a few things about E that we can write down, okay? E is the limit of n the limit as n, I should say, I'm sorry. The limit as n approaches infinity. Okay. E, we can write another bullet point right here. E is continuously compounded. So that's the kind of that symbol, continuously compounded. Okay, and E is an irrational number. So something like pi, right? The symbol of pi stands for 3.14 blank, 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 right? Well, if we take a look at our calculator and we go second, and we go all the way down to this ln button, the natural log, hit enter, E raised to the first power, because remember, anything raised to the first power is just itself. E raised to the first power is 2.718281828. So we can definitely write that down as the value. 2.718281828. So just like what this saying says right here, as n becomes really, really large, it is always going to approach this number. And then it's kind of just going to like taper out. Like no matter how large your n value gets in that denominator and then in that power, in the exponent, your value is always going to just kind of hover and stay around this value of E. Okay? So since this value right here that we've been focusing on, the continuous compound, okay, continuous growth, approaches a limit as n gets very large, we're going to use the following formula to calculate the amount of an investment that has interest compounded continuously. So the formula that we were just looking at is the formula that gets us closer and closer and closer to E. But now what we're going to be using is we're going to be using this continuous compounding interest formula that includes E in it. So it is important to recognize that the compound interest formula that we were using last week and the beginning of this week is different than the continuous compounding interest formula. The formula that we were using last week was that A is equal to P times 1 plus R over N raised to the N times T power, right? Whereas this continuous formula is A equals P times E. Okay, we just figured out what E was, 2.718281828, right? Raised to the R times T power. So A is still the amount of your investment, right? Okay, P is still that principal or your initial value. E, okay, is that value of 2.71828. Okay, we're gonna kind of learn more about E in the coming days, but E is crucial to us. And then it's also important to know, and I kind of is small, R is still the rate and T is still the time. Okay, and it is important to notice that your R value, your rate, and time, now they're both in the exponent. Maybe we can write ourselves a note. Rate and time are both in the exponent. Okay, whereas before, only your time and that N value was in the exponent. So let's go ahead and let's go through a couple of examples. Like I said earlier, we're not assessing on this topic, but it is definitely important for us to recognize that there is another type of exponential growth, and it is something that is compounding continuously. So like all of the time. Even like when you're subconsciously thinking about something, it's happening. You may not be thinking about it, but it's definitely happening, kind of like blinking, or like I said, that analog clock, right? So let's go ahead and let's look at some examples. The first